So as usual, we have our presentation here. This one might be a little longer than our typical lesson presentation. If you have any questions along the way, please raise your hand, shout at me, unmute your mic and shout at me. Let me know if you need a further explanation, anything like that, please tell me. All right, so here's chapter 11, which is inference for distributions of categorical data. And we're starting with 11.1, which is chi-square tests for goodness of fit. The chi-square test is very similar to our z-test or t-test that we've done with proportions or means, except this has to do with categories or categorical data. And how do we compare those distributions? Oh, it's not going to click if I'm not in that thing. Here we go. Clicky click. All right, so here's our objectives. After this section, you should be able to state appropriate hypotheses and compute expected counts for a chi-square test for goodness of fit, calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test for goodness of fit, perform a chi-square test for goodness of fit, which is putting all those things from the first two check marks together, and conduct a follow-up analysis when the results of a chi-square test are statistically significant. Yes, Allison.
I don't know if it's just me, but I can only see the Canvas interface.
Oops. Thank you. My bad. I should probably share the screen that I'm talking about. That one. Now you guys can see it? Yeah? Can I get a thumbs up if we can see it? Yes? Okay, cool. Sorry, apologies. So here we go. Here's our objectives again, as I was just talking about that you couldn't see, but now you can, so hooray. So again, that's what we're going to hopefully be able to do today. And let's get this going. So sometimes we want to examine the distribution of a single categorical variable in a population. The chi-square goodness of fit test allows us to determine whether a hypothesized distribution seems valid. So rather than comparing a single proportion or a single thing, like single part of those variables of the distribution, like how many blue M&Ms are in a bag, and if that proportion is, what they claim it to be, the chi-square allows us to check the entire distribution for correctness without having to do a test for each individual thing, which is nice. That saves time. We can decide whether the distribution of a categorical variable differs for two or more populations or treatments using a chi-square test for homogeneity. Right. We will often organize our data in a two-way table, so we'll see more two-way tables again. It is also possible to use the information in a two-way table to study the relationship between two categorical variables. The chi-square test for independence, which is there's two tests that we can do here, homogeneity or independence, allows us to determine if there is convincing evidence of an association between the variables in the population at large. So the chi-square test for homogeneity allows us to test whether or not the distribution is what whoever made it claims it is. The chi-square test for independence allows us to determine if there's evidence of an association between variables, right? And we're looking at it like a two-way table. So there's two different tests we can do with our chi-square. Right, so here's an example. Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&M's milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of each of the browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blue. The one-way table summarizes the data from a sample bag of M&M's milk chocolate candies. In general, one-way tables display the distribution of a categorical variable for the individuals in a sample. All right, so below we have just a one-way table showing the count of how many candies in a sample of 60 were each of the colors from our sample. So this is what we saw when we took a sample of 60. Right. We could calculate a sample proportion of blue M&Ms to be p hat, 9 out of 60, which is 0.15 or 15%. Right. If all I wanted to do was test whether or not their claim about the percentage of blue M&Ms was correct, I could just do a one sample t-test, as we've done previously. But that only tells me information about one of the colors. Okay. So again, here's our p hat. Since the company claims that 24% of all M&Ms and milk chocolate candies are blue, we might believe that something fishy is going on. We could use the one sample z-test, sorry, not t-test, for proportion to test the hypotheses. The null hypothesis that p is equal to 0.24, the alternative that p is just not equal to 0.24, where p is the true population proportion of blue M&Ms. We could then perform additional significance tests for each of the remaining colors to see if the claim for each color is correct. Performing a one sample z-test for each proportion would be pretty inefficient and would lead to the problem of multiple comparisons, meaning we could find significance in some of the results and not some of the others, and then how do we interpret that? We have like conflicting things going on. That's not helpful. Is there anything I can clarify so far? Performing one sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does, taking all the colors into consideration at one time. For that, we need a new kind of significance test called the chi-square goodness of fit test. Right? The null hypothesis in a chi-square goodness of fit test should state a claim about the distribution of a single categorical variable in the population of interest. So in this case, we have the null hypothesis that the company's stated color distribution for M&Ms, milk chocolate candies is correct. Notice that we don't have to use like p equals or that type of thing. I can simply write a sentence saying, hey, we believe that what they claimed is correct. And that's sufficient, that's enough. I could write it out that each of the individual, P of blue is, 0.24, P of red is P of and have, like 5 different variables going on, or I can just write it like this, which seems a little more efficient. The alternative hypothesis in a chi-square goodness of fit test is that the categorical variable does not have the specified distribution. In other words, we essentially write the same exact statement again, but then say is not correct instead of is correct, which again is a little easier than trying to write out all the individual parameters. We can write it out as the parameters, and we'll see that on the next screen. But at times this is a little easier and less like cumbersome, so to say. Does anyone need a moment to write any of this down right now? Please raise your hand. And so here this is, we can also write the hypotheses in symbols as the null hypothesis H sub 0, P of blue equaling 0.24, P orange, 0.2, P green, 0.16, P yellow equals 0.14, P red equals 0.13, P brown equals 0.13. The alternative, at least one of the P sub i's is incorrect. All right, and I is somewhat of a placeholder saying we can replace it for any of the subscript things. Okay. P sub I is used often as I as a little subscript to say that this will be replaced with something that I've got numbered or labeled in a subscript somewhere else with this variable. Where P sub color equals the true population proportion of M&Ms, milk, chocolate, candies of that color. So again, we can write our null and alternative hypotheses like this if we want. Also, though, keep in mind if our category has like a lot of different things in it, like this only has 6 colors. What if we had categories that, you know, there was 15 different possibilities or more? It's going to take a really long time to write it this way. The idea of the chi-square goodness of fit test is this. We compare the observed counts from our sample with the counts that we would have expected if H sub 0 is true. The more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis. Also notice, our hypothesis has proportions in it, but the things we will be comparing is the count, not a percentage. Please be aware of that. We are going to be using the actual count of things, not a percentage. Assuming the color distribution stated by Mars Inc. is true, 24% of all M&Ms, milk chocolate candies produced are blue. For random samples of 60 candies, the average number of blue M&Ms should be 0.24 times 60 is 14.4. This is our expected count of blue M&Ms. Using the same method, we can find the expected counts for the other color categories. This is the same essential procedure that we used with random variables, right? When calculating the expected value of a random variable. Basically the probability of having that thing happen times the sample size. It's exactly what we're doing to get our expected count here. And so for each color in our category, we get an expected value. There should be 12 oranges, 9.6 greens, 8.4 yellow, 7.8 red, 7.8 brown on average. This is what we should get when we sample 60 candies. And we can list these side by side here to see our observed versus expected. Right, just visually here, looking at the two tables or looking at the table on the right, we should see that we have some evidence to kind of continue with our test here. These are not the same, right? We should have gotten more blues than we saw. We should have gotten more oranges. We should have had less green and less yellow and less red, but more brown, right? The numbers aren't necessarily matching up very well, so it gives us a reason to continue. So you may have any questions? Am I going too fast? Please tell me. Okay. So to see if the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with the expected counts, assuming the null hypothesis is true. If the observed counts are far from the expected counts, that's the evidence we are seeking. We can see this in a side-by-side bar graph as one way to kind of look at it, and we can see observed versus expected. Our bars are not the same height for each color, right? That's some evidence that we're looking for. Right, we see fairly large differences between the observed and expected counts in several color categories. How likely is it that differences this large or larger would occur just by chance in random samples of size 60 from the population distribution claimed by Mars Incorporated? To answer this question, we calculate a statistic that measures how far apart the observed and expected counts are. The statistic we use to make the comparison is the chi-square statistic. This is essentially like standardizing these values. Just like we have done with proportions and means, we get a test statistic or like a standardized score. Same idea applies to this. We're seeing on average how far, what's the difference between these things. And our chi-squared statistic is a measure of how far the observed counts are from the expected counts. And the formula is as follows. We have chi-squared. Right, that's kind of like an interesting looking capital-ish X squared. It is a Greek letter, chi. And that is equal to the sum of the observed minus the expected value squared divided by the expected value. Right, so this fraction is calculated for each observed and expected value. Does anyone need a moment to write this down? Please raise your hand. Yes, okay. All right, so the table shows the observed and expected counts for our sample of 60 M&Ms, milk chocolate candies. We need to calculate the chi-square statistic. Right. And this shows how we use each observed and expected to get each of the fractions that make up our sum for the chi-square statistic. Right, we have our blue one here, 9 and 14.4. We get 9 minus 14.4 squared divided by 14.4. Right, notice we use the same value expected divided and expected here for each of the fractions. It depends on which two values we're comparing. 8 minus 12 squared divided by 12, 12 minus 9.6 squared divided by 9.6, and so on. We have 6 parts, 6 fractions that we're adding all together. That gets us 2.025 plus 1.333 plus 0.6 plus 5.16, 186, blah, 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 blah. We get all these numbers. Finally, we have a sum of 10.18. Right? This is our chi-square statistic. And very similarly to what we've done with our test statistics in the previous chapters, we need a table to deal with this. We'll get to there in a moment. All right. Think of chi-squared as a measure of the distance of the observed counts from the expected counts. Large values of chi-square are stronger evidence against the null hypothesis because they say that the observed counts are far from what we would expect if the null hypothesis were true. Smaller values of chi-square suggest that the data are consistent with the null hypothesis. Right? Similarly to like a large standard deviation means that our distribution is very spread out. A large chi-square means that we're very spread out, meaning, there's too much difference between these things. So we have evidence against the null hypothesis. But we're not done. We can't make a conclusion yet. Does anyone need a moment to write anything down from this screen or this example? Please raise your hand. So the sampling distribution of the chi-square statistic is not a normal distribution. It is a right-skewed distribution that allows only positive values of chi-squared and can never, because chi-squared can never be negative. When the expected counts are all at least 5, all right, this is a new condition. This is one of the conditions that we're going to have to check for for performing an inference with chi-square, right? It is essentially like a large counts condition, except instead of being all at least greater than 10, we're now to greater than 5 because we can have lots of categories. Right? The sampling distribution of the chi-square statistic is close to a chi-square distribution with degrees of freedom equal to the number of categories minus 1. Right, so previously we calculated degrees of freedom for sample means and population means when doing inferences with those. And we were using degree of freedom equal to the sample size minus 1. In this case, we are doing number of categories minus 1. The sample size doesn't matter. It's the number of categories we're comparing that matters. Right, the chi-square distributions are a family of distributions that take only positive values and are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. The chi-square goodness of fit test uses the chi-square distribution with degrees of freedom equaling the number of categories minus 1. Would anyone like a moment to write anything down from this screen? Raise your hand. Okay. We computed the chi-square statistic for a sample of 60 M&Ms to be chi-square equaling 10.180. Because all the expected counts are at least 5, the chi-square statistic will follow a chi-square distribution, degree of freedom equaling 6 minus 1 equals 5, reasonably well when the null hypothesis is true. And we have our little graph here showing our chi-square distribution with degree of freedom 5. Here's where our chi-squared value lies. The proportion to the right of this is our p-value. Right, that's the probability of getting a value that far away, or that from no difference, right, 0 on this graph, or more. To find the p-value, we use table C. That is the last table in your tables and formulas little set of pages. And look at the degree of freedom equaling 5 rho. Right, so we have a little excerpt from this thing here. We have degree of freedom 5 here. We're going to look across this row, and this is just a section of this. Right. The chi-square statistic of 10.180 lies between 9.24 and 11.07. Our p-value, right, is between 0.05 and 0.1. It is greater than alpha equaling 0.05. Now remember, we use alpha equaling 0.05 as our significance level when one isn't stated for us. Nowhere in this problem did they tell us what significance level to use, so we default automatically to using alpha equaling 0.05. That's why it's being used here. And that's always just going to be the default. If one is not provided, use alpha equaling 0.05. Therefore, we fail to reject the null hypothesis. We don't have sufficient evidence to conclude that the company's claimed color distribution is incorrect. Right? And so this, we're not doing this to like a confidence interval. We don't have percentages, like confidence percentage going on here. This is just a significance test, right? And table C is used very similar to table B when we're doing significance tests for population means, right, where we will fall in between two values most of the time. And so we get a range for the possible values for the p-value. We can get more exact using our calculator, but for now we're just going to use the table. Is there any questions so far? Is there anything I can clarify? So then, now that we know how to do this thing, here's our conditions for performing a chi-square test for goodness of fit. They should look incredibly familiar. It's basically the same set of conditions we're checking for everything. We need randomness, right? The data come from a well-designed random sample or from a randomized experiment. 10% condition needs to be satisfied when sampling without replacement. And our large counts condition is that all expected counts are greater than 5. Okay, so essentially like all the other tests and confidence intervals and things like that we've done, we got the random 10% and something having to do with the size of the thing we're comparing. It would be sample size, or in this case, our expected counts. Before we start using the chi-square goodness of fit test, we have two important cautions to offer. Right? The chi-square test statistic compares observed and expected counts. Don't try to perform calculations with the observed and expected proportions in each category. Not how it works. We're dealing with the count. When checking the large sample size condition, be sure to examine the expected counts and not the observed counts. These are very important points. The numbers you're going to be working with in your calculations will be counts, observed and expected. The expected counts are what we check for large counts condition. Or they call it large sample size condition. Does anyone need a moment to write anything down from this screen? Please raise your hand. All right. So we have carrying out a test, the chi-square test for goodness of fit. Suppose the conditions are met. To determine whether a categorical variable has a specified distribution in the population of interest, expressed as the proportion of individuals falling into each possible category, perform a test of the null hypothesis H sub 0, the stated distribution of the categorical variable in the population of interest is correct, or the alternative hypothesis that the stated distribution of the categorical variable in the population of interest is not correct. Start by finding the expected count for each category, assuming that the null hypothesis is true, then calculate the chi-squared statistic. Right. And this chi-squared equals the sum of the observed minus the expected squared divided by the expected, where the sum is over the k different categories. And again, k is just a placeholder variable for whatever number of categories we have in our data. The p-value is the area to the right of chi-squared under the density curve of the chi-squared distribution with k minus 1 degrees of freedom. So this is our chi-square test for goodness of fit. Does anyone want a moment to write this down? So let's look at an example. We have a problem. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it into the highest levels of the game. Specifically, since January 1 is the cutoff date for youth leagues in Canada, where many National Hockey League and NHL players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it to the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. Problem: the one-way table below summarizes the data on birthdays for these 80 players. Right, so we have across the top the birthday, which is broken down by quarters, January through March, April through June, July through September, October through December, and the number of players born in each of those months. Do these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? So our statement here, notice we're doing the 4-step process to do our inference. We want to perform a test of the null hypothesis, birthdays of all NHL players are evenly distributed among the 4 quarters of the year, versus the alternative, the birthdays of all NHL players are not evenly distributed among the 4 quarters of the year. No significance level was specified, so we'll use alpha equaling 0.05. Plan. If the conditions are met, we will perform a chi-square test for goodness of fit. Random, the data came from a random sample of NHL players. 10%, because we're sampling without replacement, there must be at least 10 times 80 equaling 800 NHL players. In the season when the data were collected, there were 879 NHL players. So that condition is good. Large counts, if birthdays are evenly distributed across the 4 quarters of the year, then the expected counts are all 80 times 1 quarter equaling 20. These counts are all at least 5. So then we do some math. The test statistic. We have our chi-squared statistic. Statistic is 32 minus 20 squared over 20, 20 minus 20 squared over 20, 16 minus 20 squared over 20, 12 minus 20 squared over 20, 7.2 plus 0.8 plus 3.2, we get 11.2. So this is what the graph would look like. We have our right skewed chi-square distribution with degrees of freedom equaling 3 because we had 4 categories in our data. And we get our chi-squared of 11.2 sitting right there on the curve. We have this little tiny sliver of p-value to the right of that. As the excerpt shows, chi-squared corresponds to a p-value between 0.01 and 0.02. Right, our 11.2 falls between these two numbers, 9.84, 11.34. We have 3 degrees of freedom. We will most likely be a little bit closer to 0.01 because 11.2 is closer to 11.34. That's just a little bit of kind of working the logic there. Does anyone have any questions about the math part of this here? So we can make our conclusion here because the p-value 0.011. So they got an exact p-value most likely by using the calculator, which they did not show, which is why they're not saying there's a range for the p-value, is less than alpha. But even if we just had the range to go by, we would know that the p-value must be less than 0.05 because between 0.01 and 0.02. Right, we reject the null hypothesis. We have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. Right, so that last example puts all the pieces together, doing the 4-step process, conducting a chi-squared test for goodness of fit. Are there any questions about this example? Sorry, Wesley, I just saw your question here. How did we get degree of freedom equaling 3? Let's go back here. So we have 1, 2, 3, and 4 categories, right? We broke the year down into quarters. So like they had January through March as 1 quarter, which is 1 category, April through like June, July through August, and so on, to make up the 4 quarters. So we had 4 categories in our distribution, in our categorical distribution. So our degree of freedom will be 4 minus 1, 1 less than the number of categories. Awesome. Excellent. All right. Stuck. There we go. All right. Is there any other questions? Anything else I can clarify on our example? So then that is the presentation here for that chi-square test for goodness of fit. This follows essentially the same pattern of our significance tests that we've done in the previous chapters, right? It's just now we're dealing with counts and things like that. We're calculating a different statistic, but after we get that, we're still using a table, finding our p-value, comparing that p-value to the significance level, and then making a conclusion the same way that we would make a conclusion with our other tests. Right? And so we saw all this except for the follow-up analysis. We'll get to that at another point. All right. So let's do that. Do that. No. Okay, yeah, that stopped. Cool. Alrighty. So that is the presentation. Tomorrow we will be doing a Desmos activity to practice some of these things. We'll practice dealing with like doing our expected counts, comparing those, calculating a test statistic, finding the p-value, making a conclusion, all those little parts tomorrow. Are there any other questions, comments, concerns, anything like that before I end the live session? All right. So then in that case, that is all that we have for today. I hope you all have a great rest of your day, and I will see you all tomorrow.